Hello. In this lecture, we are going to start off with Laplace's equation in three dimension. Previously, we have discussed Laplace's equation in one dimension and Laplace's equation in two dimension. And we have also listed, we have written two of the most important consequences, or you can say two of the most important results concerning Laplace's equation. The first one that how to find Vx, like it can be found as an average of of the neighboring points. Okay, so in two-dimensional case we wrote it as integral VDL divided by 2 pi r, and for one-dimensional case we wrote Vx as 1 over 2 Vx plus epsilon plus Vx minus epsilon. And also that we saw more generally at Vx does not tolerate any maxima or minimum, so local maximum or minimum. And if at all uh, if at all we have to say that if at all it exists, if at all the extreme values have to exist, they will always exist on the boundary. Okay, so in three dimensions, we are going to solve it. And lately, we are going to look all these things in very detail. These are only just introductory lecture. Uh, just give me a minute so that I share my screen. So here it is. Just give me a minute. Okay, so just give me a minute as I share the screen. Okay, so we've already done all these things in two dimensions and one dimension. So we are going to do it in three dimension right now. And probably today we are going to also see, if not at least one relevant example also. So here I have done all these things like we have done. That is two dimension, one dimension case we have done. Just give me a minute. It's giving me slight difficulty. Okay. So here I'm going to write. So we are discussing Laplace's equation in three dimension. So in one dimension, we saw that your Vx can be written as 1 over 2 Vx plus epsilon plus Vx minus epsilon. Okay. In two dimensions, we were able to write your Vxy. For example, let us say this is our point Vxy, and if we want to find the value of the potential at point x comma y, then this will be equal to integral VDL divided by integral d. So this is how we are going to find the average value of the potential. So this is how we are going to find the average value of the potential, and this average value of the potential is equals to Vxy. That is, if I want to write the potential at a point x comma y, if I want to write the potential at x comma y, all I have to do, I have to find the average value of the potential over the circumference divided by circumference. I'll be able to find the I will be able to find the potential at a point. So what I have to do, see, in case of one dimension, if I'm writing what will be my potential at point x, so potential at point x would be equals to half of the potential of the sum of potential equidistant, symmetrically situated to x. For example, I will just find Vx plus epsilon. I will find Vx minus epsilon, and this is how I'll be able to find the potential Vx, and that will be equals to half of Vx plus epsilon plus Vx minus epsilon. Okay, and analogous to in two dimensions, we've written that potential at x comma y would nothing be equals to the average value of the potential around the point around this V. So around V, the average value can be found because this is two-dimensional case. All we have done is we have made a circle, and we'll found the average value over the circumference divided by circumference. This will give us the average value of the potential. In three-dimensional case, Again, the same thing, same result we are going to write. But now, the average value of potential, the average value of potential V over over sorry, average value of potential at a point R, at a point R is equal to, sorry, 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 the value of potential at a point R is equal to the average value, is equal to the average value of V. Now here, instead of like drawing circumference, average value of V over a spherical surface, over a spherical surface of radius R centered at smaller. So for example, if I want to find my value of potential at a point, what I have to do, I have to find the average value of the potential nearby. So in three dimension, nearby would be constructed by an open ball, or you can say as open, you can say that you can draw a sphere. So if I just find average value over this particular surface, if I'm able to find the average value over this particular surface, I will write that this average value over this particular surface is nothing but it is equal to the potential at the center. So potential at the center is given as, if I want to draw, if I draw a sphere centered, like whose center is this particular point R, if I just find the average value of my potential over the spherical surface, what would be the average value? Oh, average value will be VdA divided by integration dA. And let us say that this is having radius capital R. So potential at point R vector is given by 1 upon 4 pi capital R square integration VdA. Is that clear? Because in three dimension, now in order to enclose this particular point, I have to make a spherical surface. And in that particular on that particular spherical surface, if I average the potential, if I average if I find the average value of the potential, which can be written as VdA integral upon integral dA, this average value would correspond to the value of the function at this particular point, whose uh, like about like whose center we are drawing the spherical surface. Are you getting my point? So this is the thing that you have to remember, that in order to find the potential at a point, all I need to do is I have to find the average value of the potential of the nearby points. So in order to justify nearby points in three dimension, I'm making a sphere. I'm going to find the average value of my potential around around the sphere. The average value of the potential around the sphere would be equal to the value of the potential at the center. Let us understand this with an example, like with an illustration that would be like you'll be able to understand what I want to say. So for example, let us consider a charge q at 0 comma 0 comma z. So I'm considering a charge at 0 comma 0 comma z, and let us first try to find the average value of potential due to this point charge over the spherical surface. What we are doing, we are trying to find the average value of the potential, over the spherical surface over the spherical surface. How we are going to find the average value of potential over the spherical surface due to point charge q? So due to point charge q, how to find? So what we'll do, we'll simply take a patch here. Let us say it is at a distance. So on the surface, it will be at a distance capital R from the center. Here it is ZR. So this will be, here if you take theta, so this distance will be Z square plus R square minus 2ZR cosine theta. So first find this average value to this point charge at an infinitesimal small patch. whose ds, I can write it as r square sine theta d theta d phi. Okay, so this is the differential, like differential you can say differential area element. Now, in order to find average value, the average value will be equals to, if I just take the potential at this particular patch and integrate all these like all these uh, see what I've done. I've taken this particular charge q. I have found at this particular patch what is the potential. If I take all these patches and integrate them up, okay, then I'll be able to find the total potential. And if I divide it by 4 pi r square, so I will be able to find the total average potential over the spherical surface. So this is 1 upon 4 pi capital R square integral, triple integral it will be your uh, sorry, double integral it would be, and where your theta is varying from 0 to pi and your phi is varying from 0 to 2 pi. You are on the surface. So on the surface, the radial component itself is capital R. So what is potential? It is k q upon distance. Distance is root over z square plus r square minus 2 capital R, 2 capital R and then z and then cosine theta. And then you have r square, you have sine theta, you have d theta, and you have d phi. And you know this r square would get cancelled. So this r square gets cancelled here. This integral d phi would become 2 pi because here you can see no term in phi. So this integral 2 pi would become simply, integral d phi would become simply 2 pi. So this will be, I think, 1 upon 2. So I'll write k q upon 2. Now you are left with this thing only. So theta equal to 0 to theta equals to pi. And this is like sine theta d theta. And I will simply multiply 2 rz and divide by 1 upon 2 rz here. Okay. And simply I'll write root over z square plus r square minus 2z. So I think this is fine. I hope I have not made any mistake till now, because if I'll make some mistake, then this will be too difficult for me to figure out. This will be 2 pi. This will get cancelled too. Okay. So overall, sorry, there will be some cost there. What I'll do, I'll simply take this as t square. So I'll take z square plus r square minus 2 capital R z cosine theta. I'll write it as t square. And this will be equals to plus 2 rz sine theta, and this is d theta. This will be equals to 2t dt. Okay, so this will be 2t dt. I'll write this as 2t dt. So numerator, I'm going to write it as 2t dt. So this is like k q divided by 4 r z, and this integral would be, I think, 2 dt, 2t dt. Here I'll write 2t dt divided by t, because root over t square is, this will get cancelled. Theta I'll write lately because this is in t. I don't want to write limits in t. That would be too difficult thing for me to do right now. So this 2t, so I'll write simply 2 root over z square plus r square minus 2 rz cosine theta. So this 2 gets cancelled overall again. So this will be like kq upon 2 rz, and this theta varies from 0 to, so if I write my theta varying from 0 to pi, if I write pi here, this will be k q upon 2 rz. Remember, I have told you many times that root over x square is nothing but modulus of z. And remember, modulus of z is x if x is greater than 0. It is equals to minus x if x is less than 0. That is, if argument inside is negative, place a negative in front so that overall it becomes positive. So this will be modulus of r plus z, and then minus modulus of r minus z. Clearly see that this z is greater than r. So obviously this particular thing can be written as z minus r. So this particular thing would be written as z minus r. So this will be like k q upon 2 rz into 2 times z, because this will be like z plus r. This will be like minus z minus r. So this will be, sorry, 2r. So r gets cancelled, 2 gets cancelled. So overall, what is the average value of the potential over the entire surface, over the entire spherical surface? The average value of the potential over the entire spherical surface is equals to what? Kq upon z. And what is Kq upon z? You can clearly see that if your charge q is located here, the potential at the center would be Kq upon z. So clearly it is equals to what? It is equals to potential at the center. So this is what I wanted to convey, potential at the center. Okay. Similar property that I'm going to do, similar thing that I'm going to do here, second property was that Vxy does not tolerate any local maximum minimum, or Vx does not tolerate any maximum or minimum. So for example, when I was doing a one dimension case, I was writing Vx plus epsilon plus Vx minus epsilon. This was how I was writing Vx. So Vx was given by 1 over 2 Vx plus epsilon plus Vx minus epsilon. And I was saying that, let's say if this is my x, here is my x minus epsilon, and here my x plus epsilon. I was saying that Vx does not tolerate any maximum or minimum. So let us on contrary assume that Vx had a local maximum. So at let's say at x naught, Vx had a local maximum or minimum, whichever suits you, at x naught. So if you are saying that my Vx was a local minimum, Vx was a local minimum. So what I can do, I can simply write Vx naught would be greater than, sorry, if I'm writing my Vx naught as local minimum, then obviously this would be the case because, sorry, my mistake, local minimum would have. So if I'm saying that at x naught, my Vx is having local minimum, it implies that in the neighborhood, Vx naught will be the minimum value. So like even if I go x naught minus epsilon, or if I write x naught plus epsilon, that is in a neighborhood of x naught, this should be true. If Vx naught is minimum, so if Vx naught is minimum, then in the neighborhood, like in the epsilon neighborhood, I can write this like Vx naught minus epsilon would obviously be greater than Vx naught. So if I add them up, this will give us that Vx naught will be less than 1 upon 2 Vx naught plus epsilon and plus Vx naught minus epsilon, which indeed is the contradiction, to the fact that Vx being a linear function can always be written as half of Vx plus epsilon plus Vx minus epsilon. Okay. So therefore, in one dimension, from one dimension, we can see that Vx cannot have a local minimum or maximum at x naught. Similarly, in two dimension also, we saw that Vxy was having something called as saddle point. Okay. And similarly, in three dimensions also, we can argue similarly. We can say that if at all this is my point Vr, and this is my potential at point which is at r vector from origin, and if this is my potential, and if it is maximum, what does it imply? It implies that if I go in a neighborhood and if I find all these equidistant points, and if I find potential at all these equidistant points, all these equidistant point potential would be less than Vr maximum. Okay. And if I do so, all these average value of potential would be what? So if I just average them up, the average value of potential would be VdA divided by integral dA, and this will be less than V maximum, obviously, because if I'm saying that if my potential is having maximum at a point, if I make a small neighborhood, a small spherical neighborhood, or you can say small spherical open wall, if I say that my potential is maximum here, so in any case, for all the points which are equidistant from this point in in a small neighborhood, all these values will be less than Vr maximum. And if I take the average value of all these points, this will be integral Vd upon V integral dA. This will be less than V maximum. And indeed, this is something that we know that we arrive at a contradiction because this we have proved equality we have proved just above. So overall understand, in three dimensions also, we can write one generalization that we wrote for other cases as well, that V as a function of x comma y comma z here, let's say, or simply V as a function of r vector, I can write does not have a local maxima or minima and the extreme values lie on the boundaries. So I think these are the same, almost similar results we've written for 2 dimensions and 3 dimension. I expect you to memorize them because this is going to help in your examination also. And these two qualitative results are more so important. At times you'll refer this thing to be written as mean value theorem for harmonic function. Probably we are going to have a small lecture on harmonic function and Earnshaw's theorem. But overall, understand this is what we have done till now. And let us take a physical context in order to understand the three-dimensional case better. To understand that, we are going to take the case of spherical capacitor. We're going to take the case of spherical capacitor. We're going to take the case of spherical capacitor. So let us consider a spherical capacitor with an inner radius of A and outer radius B. Inner radius A and outer radius is B. The inner conductor is maintained at potential phi naught, and let's say outer conductor is grounded. Okay, so this particular thing, you can see that this particular phi naught is maintained equally. So if I go around like in the direction of phi or in the direction of theta, there is a symmetry. But overall, I can see that my potential will only be a function of r, because see here you will have some phi naught, here some negative charge density is there. So you can see that this particular problem will have azimuthal symmetry as well as polar symmetry. That is, there would be no theta and phi dependence. There will be only r dependence. That is, v will only be a function of r. And if v is the only function of r, then Laplace's equation, the radial part I'm writing del by del r of r square, and then I'll write del v upon del r. This will be equals to what? This will be equals to 0. Because del square v is 0. And I'm saying that this particular potential will not depend upon theta and will not depend upon phi. It will only depend on radius. So you can see that if here you have some positive charge, here you have some negative charge, you can find that electric field will be in the radial direction. And if this electric field is in the radial direction, in order to find v, I can understand that my v would be a radial function only. It cannot be theta. It cannot be dependent on theta and phi. So if this is the case, then r square del v upon dv upon dr would be some constant k. And if I find v as a function of r, it will be, I think, some uh, uh, minus k upon r plus k2. So if I write this as k1 and this as k2, this will be it. So v as a function of r will be minus k1 r plus k2. And I know that at r equals to b, my potential is 0. And at r equals to a, my potential is given by phi naught. So if I place all these conditions, I will be able to find uh, this k1 and k2, and total potential as a function of r I'm writing, because this is something that I've evaluated already. This will be phi naught ab divided by b minus a, and then I can write it as 1 upon r minus 1 upon b. This is something that I'm giving you as a homework. You can find it using these conditions. This will be my potential. And similar to the cases previously discussed for the parallel plate capacitor and for the cylindrical capacitor, electric field can be found as minus of dv upon dr r cap here. And I think this will be equals to what? This will be equals to phi naught ab upon b minus a, and this will be, I think, 1 upon r square, and this will be r cap. Okay, because minus is already there. 1 upon r derivative is minus 1 upon r square r cap. So overall, this will can be written as this. What will be the charge density inside? Like inside the conductor, the charge density would be equals to what? Epsilon naught into the normal component. This we've done several times before also. I mean, couple of times before also. And sigma on the inner conductor will be equals to epsilon naught into phi naught into AB divided by B minus A into 1 upon A square. Okay, this will be it. So if this will be it. Okay, and what will be the total charge on inside plate? The charge on inside plate will be simply this all multiplied by 4 pi a square. So if I multiply this by 4 pi a square, I'll get 4 pi epsilon naught phi naught into AB divided by B minus A. This will be charged on the inside plate. And if I want to find the capacitance of this spherical capacitor, what it will be? It will be total charge divided by potential difference that separates, like potential difference between these two plates. So potential difference between these two plates is phi naught. So overall, the capacitance, uh, the capacitance would be 4 pi epsilon naught AB divided by B minus A. Okay, so this is what sums up our introductory lectures on Laplace's equation. Uh, if there is some certain mistake that you find, if there is certain discrepancy you find, kindly let me know. Overall, we've discussed all the three cases, that is the one-dimensional case, two-dimensional case, and the three-dimensional case, all in separate lectures. All I want you to focus on is on these two conditions. Please do understand, not conditions, I would say these two generalizations that we've drawn uh, from the Laplace's equation. So this is quite important. So kindly remember both of these results for each of these cases. And I hope further you're going to enjoy all the series on electrostatics.